Okay, we're going to be talking about Fibonacci heaps today. Um, they're a priority queue data structure. That's what they're mainly built off of. They're specialized kind of to handle graph algorithms that are similar to Dijkstra's, the one we did in class. That's kind of why I chose it, but I thought that was kind of cool. It is a collection of min heap ordered trees. And then they also have a pointer that, always points to the min element, which I will demonstrate using that San Francisco website that we use in class sometimes. And then the size of the trees follows the Fibonacci sequence, hence the name and their whole use or whatever. But why would these be used? I don't know. They aren't very popular. They don't really get used much. They're kind of overshadowed by binary heaps because they just do basically everything better. They're more like a theoretical thing that you kind of like talk about and not really use, but they're still cool and they're interesting, so who cares? And then now look at the operations that are supported. Insert, minimum, extract min, union, delete, make heap. And they're all amortized time, by the way. And a cool thing about Fibonacci heap is that the average time complexity is pretty good. Overall, everything here works pretty well, which makes you think that it'd be used a lot, but no, it is not used that much. Okay, and then this is the part where I show off how it works. I'm just using the this side because I didn't want to make slides of it. That's basically the reason. Okay, now let's insert, let's say 10. You see it becomes a min element. Then we say, let's say 11. It's going to stay the min element. And we see the links between the two. Let me just throw down the animations here. And I don't know, just for the heck of it, let's just do 15. Wow. Boom, goes there. And we do 9 where you think it's going to go. Right in the middle. Yep. And then let's do 3. Right in the middle again. One last time, let's just do 1. And it's just gonna see that the min element stays when you're inserting into a new min element in. It's gonna kind of move everything aside, go to the middle, keep everything kind of balanced, but it doesn't. Fibonacci heaps do not need to be balanced though. That's a cool thing about them. Like if you look at both sides, it's usually here it's pretty well, but if you look at a graph of it, it's not gonna have to look like that, which I'll show. I'll do that. I'll show it. Yeah, I'll do that. Alright, so I drew out a proper tree that kind of shows off what I was talking about. Here we see 2, 12, 38, and then what? 19? It's just showing how Fibonacci heaps, they don't necessarily need to be balanced or ordered. That's kind of like a trade-off that they let go for faster inserts and decreased key operations. So using those, they actually a lot useful for what I said, Dijkstra's, because faster inserts and key operations. It's kind of like a lazy data structure, I'd say. That's what I've read, but that's what people say. They keep most operations over one time, but when they're kind of cleaning up, that's when the most of the work gets done. So it kind of just makes everything a lot slower at that time, which is why binary heaps are just used a lot more because Fibonacci heaps they're just they're just not as good to use. All right, let's get to this part. This is the coding part, or not really coding. I already made it. So here we have the struct fib node with key, and then fib node next, which the next is just going to be the pointer to the next node in the circular root list here. Then let's move on to the class fibheap. We see that we have min here, which is just it tracks the minimum node in the heap. This is going to be crucial for get min and other parts in insert that you'll see. Now we get to the fibheap, which is just going to be we're just making the constructor, which is initializing min as null pointer. Then we have our insert operation here, which allocates a new node with the given key. And let's see what we have. If the heap is empty, then the new node becomes min, and then it points to itself. You see it here. That means it's showing off the circular root aspect of this. And then as for the else statement here, we have if the heap has nodes, insert after min, and then update min if the new key is similar. They're kind of, it's not anything complicated here. I'm just, once again, this is really basic here. You kind of just like stripped away all of the, this is just really bare bones here. So, and then now we have get min, which I mentioned before, which it returns the minimum key or -1 if it is empty. And then now we're gonna see here, I put in 5, 2, and 8. We inserted in 5, 2, and 8, and then we're gonna see that if I run this, it should output 2. CVP. Oh wait, wrong thing. I don't know why I did fibheap.cvp. There you go. Minimum value is 2. Boom. And then I did want to also talk about why this kind of just shows what Fibonacci heap is about. Is that it shows that how I mentioned earlier, the lazy insertion strategy that's going to be for insert. And then it also maintains the min access via pointers, and then it also uses the circular root list, which is a big point here. And I think this is kind of like the simplest possible code I could think of. I'm still learning about this, so I don't, this probably isn't perfect about it. So yeah, thanks for watching. I don't have much to say, just have a good day, have a good summer.